Hey, my name's Manish Mehta. I'm at Marshall Aerosciences. I'm just going to be quickly talking about Marshall Aerosciences PSI activities. If you go to the next chart, uh, I won't go into this at all because it's been covered at least 100 times. But the main focus of this talk is on erosion physics. Just really some of the erosion activities that we're doing at Marshall. It's mainly looking at highly underexpanded plumes, and there's looking at various different erosion mechanisms that have been kind of talked about with the different authors. If you go to the next chart, we're trying to tackle this in a couple of ways that, and Greg Shallcross kind of mentioned using an engineering approach. And that's kind of the focus that we are taking and taking here as well. So some of the methodologies that we're planning on pursuing in developing a PSI erosion model is it's got basically 6 steps. Um, the first is we have to have a test series, right? Geared toward a system that is targeted to a system that's being used to land on the moon. That's the first thing. So test series will evaluate a range of nozzle heights and operating pressures, and like I said, it's tied to an engine performance and using approved lunar regolith geotechnical simulants. So if you don't target at least for this model to stay true, if you don't target a specific system, it becomes more challenging in developing an erosion model, and I'll kind of talk about that here as I go forward. So each test will measure crater profiles, ejective properties, right, at different times during the engine operation. Uh, some some of the things that make this model really critical is you need to kind of match some of the most important first order parameters, plume properties such as density, gas velocity, temperature, composition. Uh, are definitely players, but more important players are like surface profiles, right? Pressure, shear, regolith properties are first order, as well as ambient pressure. So those all have to be really close to our flight regime um, to reduce uncertainty. So once we have the data, we then convert the crater profiles and ejected data to, as you would expect, crater depth, radius, and volume, erosion rate, and eject energy flux um, for each altitude and test point. And so keep in mind that I think Dr. Wesley Chambers mentioned the ground tests that we are performing at Langley. Those are static tests, right? We're not dynamically descending, so they're set at various set points. Then we scale the results. We look at gravity, we look at other effects, and then we build a table to apply to a flight to descent trajectory and engine performance. And then we can combine and interpolate the table based on the descent trajectory that we have to output a final crater profile. So if you go to the next chart, this is one method that we're trying to employ, and is first you have to have data, right? You got to get data from a test. We normalize the data, the subscale ground test static data. We normalize the erosion rate with the engine mass flow rate, and then we normalize the altitude with exit diameter. That's a very historical approach. And so you get a profile. You then know whatever vehicle it is, that's descent trajectory, and the engine operating conditions. You can transform this non-dimensional space into a dimensional space replicant of for flight, right? And so you have E dot as your erosion rate, and as a function of descent time. You take the integral of E dot dt, basically your colored version, underneath that curve to kind of get your crater, your actual volume, the volume of the underneath the nozzle. And then we assume paraboloids or n paraboloids. So basically, you have the first equation. E dot over rho G, and then you have the crater aspect ratio, and then you have basically two equations and two unknowns, and you can solve for your final crater radius and final depth, crater depth. And so we applied this approach with Landon Clark. It was a highly underexpanded plume. Keep in mind it was sand, not lunar regolith. We compared this with Apollo data. And keep in mind this is just one data point, and we all know that Apollo data has some quite a bit of uncertainty in the erosion, mass eroded, as well as crater depth and diameter. But we did see good agreement. And so we're planning on using this approach, but the one thing we are planning on that we need to do is we need to scale for gravity. So this accounts for scale, but we need to account for gravity, and that's something we are on plan on doing in the future. So the next chart goes into exploring non-dimensional terms, right? What are the non-dimensional parameters? And Dr. Shallcross kind of mentioned the Pi-Buckingham theory. That is one approach. Another approach is you get a set of data that you have in hand, and then you go ahead and try to determine what are the historical characteristic non-dimensional terms and how do they scale, and how do the correlations agree. And so here you have normalized erosion rate versus jet expansion ratio. All jet expansion ratio is that it's your P exit over your P infinity. So as you can expect, right, as your the plume expansion ratio increases, your impingement pressure decreases. And well, guess what? That has a first order effect on erosion rate, right? Normalized erosion rate. So you can kind of see this asymptotic distribution, and we see this for various different granular media. This is MDS is just one of them, monodispersed sand. The other one that we saw was densimetric crude number, which has been historically characterized in the past as well. Landon Clark had done it back in the 60s. We see it with relatively new data here from PFGT. Basically, you're in two regimes, right? When the particle diameters are large, you're weight dominated, right? And so your normalized erosion rate will decrease. As your DP gets smaller, your cohesion value goes up, right? And so your normalized erosion rate once again decreases. And we saw that at least for the PFGT data, we found that the particle diameter that we saw most erosion was around 100 microns, on that order. So we're investigating the dependence of gravity on erosion rate, and we're looking at other correlations with non-dimensional terms. So if you go to the next chart, and as I think a lot of the folks in ER42 have mentioned, we use loci chem as well to understand the gas flow aspects of PSI. So we provide Plume-Surface distributions such as pressure, shear, heating, and gas temperature for various ground tests that we're supporting in flight programs. We also have recently started looking at CFD gas flow streamlines to investigate dust trajectories, because we want to understand where the dust is going on the vehicle, and what the dust wetted surface area is on the lander within the Stokes regime, right? So we're also, as I think others have mentioned, you can run this time accurate and with finite rate chemistry. So we are using this tool along with the test data to get a better understanding of the PSI effects for various programs. So if you go to the next chart, this is a simulation that Dr. Chris Morris has developed, looking at pore pressure and fluidization effects due to a plume interacting with granular media. So we use the classic Darcy's law, and Darcy, a famous paper published by Scott and Co. But if you play it, if it's able to play, I know there are issues with that, but if you're able to play this video, I don't know, Addie, if you're able to, but you can very quickly see. So his simulation shows the pressure distribution as a function of time, right? As you get closer to the surface, the pressure distribution goes up. And accordingly, the domain here is using what we call, I think, as the Disney, are the Disney regolith properties, mainly from a permeability and porosity perspective. But here you can, in the middle plot, in the top plot, you can see the pressure distribution. In the middle plot, you can see the pore pressure distribution, which is a very important term for fluidization. And then the bottom plot is your fluidization parameter, which is your pressure gradient over rho g, which is your weight term, right? And you can kind of see that fluidization parameter does lead to fluidization of the granular media, allowing for cratering. So this is another tool that we plan on using to understand diffusion-driven processes. If you go to the next chart,
we may need to move to a summary chart if you have one.
Okay, yeah, I do. And then this is just flight reconstruction capabilities, and we are actively doing that to get ground truth. So we can actually measure the crater topography to look at for various landers. And so we're on the hook for HLS and a lot of the CLIPS landers to look at what is the final descent crater topography at the end. And then in the back, in the last chart, I mean, it's basically what we're focusing a lot on test and flight data derived engineering models. We're using gas-phase CFD, and we are looking at post-flight imagery, reconstruction work. And there's just a lot of PSI research that we're doing, and we're supporting, as you know, HLS and CLIPS. So that's all I have to say. Sorry about the initial. I was having internet issues, so I apologize for that.
No worries. It's going around today. Thank you. All right. So that takes us into we planned a little bit of a buffer time here / a really brief discussion period. So I think we have about 10 minutes-ish. Unfortunately, most of our speakers from this afternoon are still in the panelist section, and we can sort of bring some of the other speakers from earlier today up if that would be helpful.